I welcome you all to this lecture on microscale transport process. Here we are going to discuss various components of lab on chip. As we mentioned in the last class that there are several components we must have in a lab on chip device. These components are supposed to be pumping, valve, separation, mixing, diffusion between layers, heating and detection, and there could be some other components also depending on the application that you are looking into. And in all these components, one essential feature is that it is assumed flow is laminar. In fact, flow is very much in fact, the Reynolds number is pretty small in flows in microchannels. Flow is considered laminar and the interaction between layers are utilized in most of these components. So, this is unlike a typical flow in a channel where there could be turbulence and there could be movement of eddies from one place to another. That is absolutely missing, because you are relying on two layers flowing like a pack of cards, one sliding against the other, and diffusion is taking place from one layer to the other. So, you are relying on this laminar flow, that is for certain. So, these are some of the things that you should remember. Now, when it comes to pumping, of course, you can have a pump that we have in a conventional sense. For example, you have seen centrifugal pumps where you have an impeller rotating. Now, having such components in a microscale is not something very easy. Of course, it is doable, people have done it, but it's not very easy to implement. So, people have looked for other alternative routes that they can use to implement a pumping action, and the actions that they have is I have categorized them. One is centrifugal force. Okay, how does centrifugal force works? Suppose you have a CD type device. Suppose you have a CD device. Suppose you have a CD device, all right, and in this device you have this the sample that is going in, that sample goes in through the center. So, you have a CD type device which can be put on a turntable and it can rotate. Now, and it is a plate in which you have carved channels in radial directions, in various several channels in radial directions, and in some of the places you have reagents stacked, reagents put there, and you introduce the sample at the center. Then what you do is you rotate the turntable. So, as you rotate the turntable, because of centrifugal action, the fluid will start moving towards the periphery, right. So, this is an action that you can have. This is an action that you can have for pumping fluids. So, you have a CD type device on which you have channels carved, and on top of that you have a lead, and everything is happening in microscale. Put the CD device on a turntable. If you introduce the sample at the center of the CD and rotate the CD, automatically the fluid will move towards the periphery. So, this is a centrifugal action that you can rely on for pumping fluids, because you can control the spinning rate, you can control the RPM, and by that you can control at what velocity the sample would be flowing towards the periphery, all right. So, this can be a device. Similarly, you can have surface force. How would that force look like? You have all studied capillary rise. If you dip a glass capillary inside water, there would be a rise of water through the capillary. How does it happen? That liquid has a weight, but that weight is balanced by surface tension force, because glass is hydrophilic. So, you have the surface tension force is balanced, the weight of the liquid is balanced by the surface tension force. So, surface tension can raise water through certain height. Now, if you have a tapping point, because anyway you are working with small scale. So, if you have a tapping point, little above the water level, you can have a continuous flow of water. So, this is basically a surface using surface force to pump a fluid. Next, you can have what you can have is electrokinetic force. Electrokinetic force means you can have electrodes put there, and you can mobilize the charges, and with the charge some bulk liquid is also dragged. We will discuss this electrokinetic force in detail later. And mechanical, of course, you can have actual movement of, I mean something similar to a centrifugal pump or a reciprocating pump. You can have a moving element inside the microchannel, that is also a possibility, but other elements are very much pursued, other elements are very much looked into for pumping fluid. The next item is valve. Now, of course, you can have valve in a the way you have in a conventional sense, like you have a valve seat, you have a closure of the valve, you have another element that goes in and sticks to the valve seat, and so you consider the valve to be closed. So, you can have such elements designed, such elements implemented in microscale, but that is not again very easy. However, other ways people have looked into, and one is having a hydrogel layer, because hydrogel has some unique properties. It can respond to pH or thermal trigger. Either it can contract, it can contract as well as it can expand depending on the external trigger. So, if you put a hydrogel pillar at the channel inlet, and if you put a trigger from outside, and by that trigger you can shrink the gel layer or you can expand the gel layer. So, by that way you can block a channel or open part of the channel. So, hydrogel can act as a valve in that case. Also, there could be something called hydrophobic layer. If you have a hydrophobic element, on the wall, you know that the contact angle, if there will be adverse contact angle. You might have seen already when we dip glass capillary in mercury, how the interface would be. So, that gives you an example how a hydrophobic layer would have, how a hydrophobic surface would be acting towards water. So, if you have an aqueous solution and if you put a hydrophobic layer, then because of this surface action, because of this surface tension and contact angle, you may have to cross a threshold pressure, and then only you can have a flow through the channel. So, a hydrophobic layer, a small hydrophobic layer put on the channel wall can act as a valve in a sense. The third element that we have here is separation. In lab on a chip device, you need to have separation accomplished, and for that there are various techniques that are available. First, I would like to talk about what is called field flow fractionation. It can be of various types, for example, electrical, thermal or flow. The field flow fractionation, the way it works is, suppose for example, I look at say field flow fractionation of flow type. Suppose you have a channel and on the wall you have a membrane placed. On the wall you have a membrane placed. I said that the flow would be laminar. So, the velocity profile would be parabolic like this, okay. And there is this membrane. So, if you have solutes inside this, I mean the liquid that is flowing within the channel, if that has solutes, then the solutes would be as you collect fluid from this side. I mean, so you have a flow down this way, and at the same time you have some collection of fluid at a very low rate. You are collecting fluid from this side, okay. So, when you are collecting fluid, collecting the solvent through this side, and you are having solute being deposited, what you eventually have is something called a concentration polarization. By that what I mean is, you will see that the particles that are being held on the membrane surface if the particle is smaller, it will have a larger diffusivity and it will be easy for that particle to go to the bulk, move to the bulk. The particle that is being restrained by the membrane, if it is small, it can go to the bulk easily. If it is a bigger particle, it would be difficult for that particle to go to the bulk. So, depending on the size of the particles, you will see a classification here. This is something called a polarization. You will have particles of certain sizes held next to the membrane and particles of other sizes are more close to the bulk, I mean more towards the center. Now, you are introducing a parabolic velocity profile from this side. So, that means this layer is moving faster than the other, this layer is moving little slower and this layer next to the wall is moving at the slowest at the smallest velocity. So, if you put something called a fractogram, if you analyze the effluent coming out of this, you will find peaks coming like this, and each peak represents particles of certain size. So, you can classify the particles. Now, suppose if you have this device already calibrated with a known mixture of particles, and then if you introduce an unknown sample into this device, and the output that you get, if you look at it vis-a-vis the one that you have, the calibration that you have, you can figure out what are the various components that are what are the various sizes that are there in this fluid. So, this separation, this can be done, this is referred as field flow fractionation of flow type. Now, here the flow has been put as a transverse gradient. Here the flow has been put as a transverse gradient. Now, for other types of field flow fractionation, for example, the thermal one, there you have a thermal gradient in the transverse direction, or electrical field flow fractionation, there you have this electrical gradient transverse to the flow direction. So, by that way you can separate particles depending on their sizes or depending on their properties with the distance from the wall. And since you have always a parabolic velocity profile, I categorically said that you are relying on laminar flow in the microchannel. So, you can get layers, one layer at a time, middle layer first, because that is moving at a highest velocity, next layer and then the other layer. So, you can separate the particles, you can get a fractogram with particles arriving, eluting at the outlet at different times. So, you can classify them. Similarly, there are other separation components, like you have these electrophoresis, dielectrophoresis or dielectrophoresis plus field flow fractionation. We will discuss these in details. In electrophoresis, you have put electrodes and you apply electric field depending on the size and the mobility, depending on the mobility of the ions, that means size and charge of the ions, you can separate the you can put it will be more close to the electrode or away from the electrode depending on the mobility of that ion, mobility of that charge. So, you can find out what then if you study them. For example, in electrical field flow fractionation, I will discuss this later, that you impose this electric field in transverse direction. So, depending on the mobility of the ions, they will be located either next to the electrode or away from the electrode at various locations. And since you have the laminar flow taking one layer and the next layer, so you will be collecting the particles at different times, and so you can always using a calibration, you can always figure out particles of what sizes were there or what mobility were there in the original sample. Then there is this diffusion based separation, which is referred as H filter. It depends totally on diffusion, it does not have any electric field involved. I will discuss this, I will draw a picture very soon. So, these are some of the separation components. So, if you think of conventional chemical engineering applications, there are separations possible, but when it comes to microscale, you are relying more on this laminar flow and relying more on this parabolic velocity profile and some diffusion or certain response to electric fields. So, these are some of the things that you look into. Of course, you need mixing in microchannel, and mixing is in a traditional sense, in a macro scale, it is done using an impeller, using a stirrer. Here that is possible, you can have a stirring element within a microchannel, but implementing it in microscale is not very easy. So, there are alternative routes people have looked into. One is say passive mixing device using grooves or laminations. You have already heard of these passive mixers. That means, you have two streams flowing through a tube, and then you have several baffles placed on the way. So, that two streams they come together and then they diverge. So, by that way you increase the contact area between the two streams, and so you enhance the mixing. So, these are some of the elements that you would look into when it comes to mixing in micro scale. Then there is diffusion between layers, which is very important. I will discuss this very soon. What is a T sensor? In T sensor diffusion, people rely on this laminar flow or parabol or one layer sliding against the other. That means, no cross flow, no eddy formation, and then the diffusion from one layer to the other. This is people are relying on this, okay, to develop sensors. So, this is a T sensor we are going to discuss very soon. Then there is this heating component also you should have in a microscale process, and heating component, one heating requirement I have given an example here, cyclic heating for PCR reaction. Okay, this requires heating in steps. Within a very short time you have to accomplish several up and down in temperature. That means, you increase the temperature by certain degrees and then you decrease it, again you increase, again you decrease, again you increase, again decrease. So, you have to do, these are called thermal cycles, and you have to expose the sample to such thermal cycles, several such cycles, okay, within a very short time. And typically, if the mass is more, then accomplishing these cycles will not be very easy, because if the mass is more, you think of it, what would be the heat requirement? What would be delta H? Heat requirement would be mass into specific heat into delta T. So, if delta T is known, specific heat is known. So, if you have a large thermal mass, so you have to inject so much of heat, and that heat has to distribute through the entire material, okay, and then the temperature has to uniformly rise everywhere within this material, and again you are cooling it down, and you are doing it 20 times within a very short period. So, that is very effectively done in a microscale, and that is what I referred as cyclic heating for PCR reaction. There are of course, all these after all these microfluidic elements, microchannel devices, a major application is in sensors. So, there has to be some detection element involved. This detection is done either by optical method, okay, optical interrogation, or amperometric sensing. That means, you find out the conductivity of the fluid that is passing by. So, for example, you have classified the sample, you have a sample and you have classified it into several components, okay, and you had this parabolic velocity profile. So, one component is eluting at some time, and then the next component, then the next component, it comes like this. Now, if you want to identify those components, one could be this optical interrogation, optical detection. The other way to do it is by amperometric sensing. That means, you find out what is the conductivity of the sample that is coming out at a particular time from the outlet, and from that you can generate a fractogram. So, these are some of the elements that you have for lab on a chip device. Now, let us look to this quickly. This what are the pumping elements that we have here? First of all, use of moving part as in a conventional pump with the help of micromachining. This can be done. There can be a moving part, but this is not the only way to do, and this may not be very easy to accomplish. So, there are other methods which are in demand here. Centrifugal force to drive fluid through channels in radial direction, which is referred as lab on CD. This is used in certain industry. This lab on CD is used. So, these are these I have discussed here. The third one is use of coating with favorable contact angle and pillars in the channel to enhance a capillary rise type flow. So, you can in a channel you can have favorable contact angle, as I said, capillary rise of water in a glass capillary. Now, one thing is there, the capillary diameter has to be I think what we have studied is it should be less than say 5 millimeter, or there was a threshold. I mean, if you cross the diameter, you see this capillary rise is not substantial. So, you can so what you can have is to induce this capillary rise or to induce this surface tension driven flow, you can introduce small pillars in the channel. So, that means if this is the channel, if this is the channel, within the channel you can introduce small pillars. So, these pillars will provide extra surface area, so that you can have enhanced flow. The fourth element what you have here is electro osmosis. I said electrokinetic pumping, right. So, electro osmosis, it is basically like this: a polar liquid in contact with solid wall induces surface charges, which in turn influences migration of charges within the liquid near the wall. A voltage gradient along the length of the channel pulls the charges and a bulk liquid along with it. What you have is you have a wall and you have electrodes placed here. Okay. Now, polar liquid in contact with solid wall induces surface charges. So, surface is where? This is the surface, this is the wall. So, this is the surface. On the surface there are some surface charges generated, say I write plus. We will discuss this later, we will get into the theories of it. If you have certain charges induced, so automatically this polar liquid in contact with solid wall induces surface charges. So, the negative charges within the liquid, they will start getting accumulated on the wall, all right. And then these electrodes, they will be pulling these negative charges, say. While pulling it, it will pull the bulk liquid along with it. So, that is how you will generate some flow. Of course, the channel, these walls should be very close to each other. I mean, if you have a large pipe and if you expect this kind of flow to take place, that may not be very that may not be very much possible or feasible. The other element that we have is electro wetting. Here, the change in contact angle of a droplet on a surface when an electric field is present at an interface. I have suppose the wall and on which I have a droplet sitting there. This is a droplet. Now, if I introduce some voltage difference or if I introduce an electric field, I will find that this contact angle, this contact angle changes if I introduce an electric field there. So, if this contact angle changes, so then this would be more spreading. For example, this was the liquid and later on when you bring in the electric field, the liquid cannot grow, but the volume remains same, but the liquid the contact angle will be different. Okay. So, if you have an arrangement where you have suppose one ground electrode on top and several control electrodes in the bottom, okay, and suppose you have a droplet sitting here, a droplet is there and you apply electric field using the electrodes. So, this would be more spreading, and while this droplet spreads, it will go to the next it will touch the next electrode. Then what you do is you switch off the, see you have these electrodes are they can be controlled separately. So, you switch off this electrode and introduce electric field through this electrode. So, automatically this droplet will be picked up by this electrode and the same process will continue. So, you will see this droplet rolling down, this droplet would be rolling down through these electrode assembly, all right, by this phenomenon. So, that is what exactly what I mean by this electro wetting here. The change in contact angle of a droplet on a surface when an electric field is present at an interface. A droplet is held between two sets of planar electrodes, I described here, two sets of planar electrodes. Upper one consists of single continuous ground electrode and the bottom one with an array of independently addressable control electrodes. By spreading the droplet using the electric field such that droplet touches adjacent electrode in the array and then switching on the adjacent electrode, movement of droplet is accomplished, all right. So, this is one method by which you can move a droplet within a microchannel. Next, what we want to discuss is a T sensor, because this is some element which you have probably not seen in macro scale. This is a unique device, but this became once upon a time, this was very popular in microfluidic literature. This T sensor, it is basically nothing but a channel, it is nothing but a channel through which there is a provision for two liquids to enter into the channel. Two liquids can enter into the channel. So, ideally you expect the liquid to be moving like this parallelly, right, like the two layers they are moving parallelly. So, this is ideally, that is what you expect. This is just a channel with two liquids introduced. So, they will be moving parallelly, one layer sliding against the other. Now, if you allow diffusion to take place in between, then you expect, suppose one is say having red color and the other is colorless and one can mix with the other. So, in that case you can have the color moving from one layer to the other. So, if the red color is, if this is say red colored and this is say black, this is a black colored, you will find there would be some amount of diffusion. So, the interface would be a little blurred, because one layer will diffuse into the other, all right. Now, what you have in a T sensor here is that you have a sample stream and other stream. So, one is your one is sample stream, one is sample stream, and the other stream I am calling it say other stream. Okay. Now, sample stream contains sample antigen that you want to measure and also a fluorescently leveled antigen that is kept to a concentration 2 to 3 orders of magnitude less than anticipated sample antigen concentration. So, you have a sample stream that contains sample antigen and a fluorescently leveled antigen which we refer as LA. So, there is SA and there is this LA. So, one stream, that is the sample stream contains SA and LA. So, SA plus LA, that is what sample stream contains, and this other stream that contains a known concentration of antibody AB to the target analyte. So, what that means is I want to find out what pathogen is there in a sample. So, I have several antibodies present and I would like to find out which antibody goes with the sample. So, I say I have say 5 antibodies and I know 4 will not go with the sample, the only one will go with the sample, that is the target, but that I do not know. I do not know what is this sample antigen. So, sample antigen is something which I do not know and I want to find out what is this sample antigen. So, I have introduced some amount of fluorescently labeled antigen, okay, that is LA, which I introduced with the sample stream, but its LA concentration is very small, and then I am having these 2 streams flowing side by side through this channel. So, the implication of this is that AB molecules, these antibody molecules, they are larger and slow to diffuse. Now, AB binds with all LA if SA is not target analyte. See, AB binds with LA, AB binds with SA only if that is the corresponding AB, because I have 5 such ABs present, 5 such antibodies present, out of them only one can bind with SA, others will not. All right. So, AB binds with all LA if SA is not target analyte. So, bound LA cannot diffuse into AB stream once this LA is bound with the AB, because AB is a bulkier. So, color stays near interface, because LA gives you the color, LA gives you the color. So, so color stays near interface, because LA which gives the color, that is bound with the bound with AB, and AB is a bulkier molecule. So, it cannot now diffuse. So, it will stay next to the interface. AB binds with SA and some LA if SA is target analyte. So, if SA is target analyte, because SA is there in very large quantity. At the very outset I said that LA concentration is intentionally kept 2 to 3 orders of magnitude less than anticipated SA concentration. So, in the event SA is the target analyte, so if in the event the AB binds with this analyte, so in that case there will be lot of free LA available, okay, and this and free SA as well, because AB is only in fixed quantity, and if this is binding both with LA and with SA. So, there would be free SA, free LA available, and these can diffuse into AB stream. So, AB stream means which stream? The other stream. So, I had originally sample which is SA plus LA, and I have another stream which is AB. Now, 2 are moving side by side, okay, and then I will find that in most of the cases there would be this is the color. So, this color is penetrating, maybe this is more deep and this is light. So, this part is probably lighter, but there would be a penetration of color into this other stream, which is predominantly AB. This penetration of color is possible only if this SA, if the AB that I introduced is actually it corresponds to the sample antigen, but this penetration of color is not possible if this AB that I introduced is not, it does not correspond to the sample antigen. So, I have several such channels in place. I have several such, and suppose I can assume, okay, this is my sample and this sample can contain say 10 such pathogens, it is possible. I want to find out which one is present there. So, I have the target, so I identify the target antigens and I get the antibodies and I put them in place and I flow them side by side, and I find in one case there is diffusion of color deep into that other stream, deep into the antibody stream, and in other cases the color remains mostly next to the interface. So, from that I can figure out which one is the target antigen. So, which pathogen I have in this sample. So, what we have here is that I said AB binds with SA, lot of free LA etc., and spread of color into AB stream. More than one tin sensor in the chip with different AB to target analyte, spread of color can be determined digitally. You can have an light source, you can have a light source and you can have a detection element placed on the next to the wall of the microchannel, and from that it can sense it digitally. It can go through some algorithm and it can tell you, okay, this is the pathogen directly from that scanner. I mean, you do not have to look at this and find out, okay, how much the red color has gone in and make decisions on your own. It is not that way. You can acquire the data digitally and have a software to analyze this and software to tell you, okay, this is the pathogen. So, this is a device which can be used to find out which pathogen is there in a sample. There is another element of interest here, I mean, which is unique. These elements are unique. I mean, we thought that we know about flow and macro scale processes, but in micro scale processes there are some simple elements that can do a lot of important work. Here you have two parallel laminar streams. Two parallel laminar streams will flow. One is the sample stream, such as blood containing aggregates of different sizes, and the other is acceptor reagent such as saline water. So, what you have in this case is you have a channel through which you have two streams flowing, and they are flowing parallel to each other. One is blood containing aggregates, aggregates of different sizes, and the other one is saline water. All right. So, you have these two streams flowing side by side. The smaller molecules, the smaller components, smaller particles in blood, that you will find that will be very easy for these particles to diffuse into the water stream, whereas larger ones, the diffusion will not be easy. So, if you collect these two streams out, what do you have? You split the two flows into two reservoirs. So, what you find there is the upper stream that will contain blood without the smaller particles or smaller aggregates, because smaller ones have gone to the saline water. So, if you want to separate the smaller ones from blood, or if you want to concentrate the blood or focus on the bigger particles within the blood, so you can have such a device. So, I said at the very outset that these laminar flow and diffusion between two parallelly flowing layers, these would be used in several elements of these microscale devices, and they do a very unique and very useful job. We discussed about this detection. We said there are two types of detections possible. One is this optical interrogation, that is what we said, laser induced fluorescence system, and the other is the electrochemical method. In case of laser induced fluorescence system, fluorophores are conjugated with migrating analytes. Laser beam excites the fluorophores. Resulting fluorescent signal is filtered to block background illumination from the excitation source, and fluorescent signal is recorded using CCD camera. What this means is that you intentionally put a fluorescing, you intentionally put some fluorophores, they are conjugated with migrating analytes. That means, I have a channel, okay, and I have some analytes flowing through this, okay, and I am introducing fluorophores that are conjugated with migrating analytes. What that means is, suppose I have say calcium ion, okay, and that calcium ion I want to identify. So, I introduce a fluorophore which would be I introduce a fluorescing agent that ties up with calcium, all right. So, they ties up with calcium, and then what we do is we put a laser beam we put a laser beam. So, we put the beam here, and within this beam, say I put a laser beam, I illuminate this layer by using a laser source, using this light source. I illuminate this layer, okay, and this is continuously, this stream is flowing through this. Okay. So, I illuminate this layer. I illuminate this layer means I produce a light of certain wavelength. That is what the purpose of laser is. It will produce light of certain wavelength that will go and hit the fluorophores, and you get the light, you get a fluorescent signal which is probably at a different wavelength, and that signal is captured by a photo detector, say or simply a camera. Suppose this is a camera, okay, by a CCD camera, by PMT, photomultiplier tube, or APD, which is avalanche photodiode. By some photo detector you detect the light that is emanated, that light that is coming out from these fluorophores. So, you intentionally add some chelating agent that ties up with the ion that you want to measure, say calcium ion you are measuring. So, it ties up with calcium, and then you find out what is the then you introduce a light of certain wavelength, and you know that the light, this light will, when it hits these fluorophores, you will get a fluorescent signal of certain wavelength. Now, on this camera or on this photo detector, if you have some kind of screen, some kind of filter to block the illuminations of other wavelengths and only focus on that particular wavelength which these fluorophores can generate, then you can get a fair idea what is exactly the concentration of the sample that you have. So, you have this resulting fluorescent signal is filtered to block background illumination from the excitation source. Fluorescent signal is recorded using CCD camera, PMT, or APD. So, this is a laser induced fluorescence system. These particular this laser source and the detector, etc., these would be a part of the scanning device. So, these may not have to be a part of the micro channel, but this would be next to the micro channel, and if this microscale this wafer, if this is optically transparent, then it can be held, the laser, that light source and the detector can be held next to it. Now, there are other methods as well. For example, these electrochemical methods is also there. In this method, what is written here is monitor variation of electrochemical properties as analytes migrate past a working electrode positioned within the separation channel. The conductivity is related to the concentration of species. That means, in the channel you have electrodes positioned within the separation channel. So, you have electrodes positioned within the separation channel, and you find out the conductivity as this quantity. Here this lambda plus, these and lambda minus, these are limiting ionic conductance, limiting ionic conductances in solution. C is the concentration, K is the cell constant, K is the cell constant, that is basically the L is distance between. So, this is basically distance between electrode pairs divided by the electrode area. So, by looking at this conductivity and by having a pre-calibration done, you can figure out which component is eluting from the channel at what time. All right. So, you can identify the components. I mentioned about this electrophoresis as one of the separation element. What we have in this electrophoresis here is that migration behavior of charged species under the influence of an electric field. Here analytes are suspended in an ionic buffer element at a specific pH. Each species migrates with a different mobility, allowing them to be resolved as distinct zones and separated on the basis of size and charge. Biological macromolecules such as proteins are analytes. What we are talking about here is basically I have two electrodes, and in between I have this sample. So, I have say one ion here, it has a size, it has a charge, and depending on what size and what charge, it would be attracted towards certain electrode. Okay, so, that is what we are talking about, migration behavior of charged species under the influence of an electric field. Analytes are suspended in an ionic buffer element at a specific pH. So, the pH is this is done at a specific pH. Each species migrates with a different mobility. Now, these particle would be experiencing what? These particle under this electric field, it would be pulled, and at the same time there would be a drag experienced by this particle. Okay. So, depending on so there would be a force balance, drag and electrophoretic mobility, they are counteracting forces, and typically gravity is neglected. So, each species migrates with a different mobility, allowing them to be resolved as distinct zones. So, if you start this process and maybe freeze after some time, take away the electric field, what you will find is these particles, they have rearranged, they have repositioned themselves depending on their mobility. So, this is one way of say forming or resolving this sample as into distinct zones separated on the basis of size and charge. So, you have distinct zones. Suppose this sample contains A, B, C, D, E, F, G, H, out of them A, H and K, these belong to the same category as far as the size and charge is concerned. So, they will band together in one location. Some other components, they will band together in another location. So, that would be eventually, that is what is going to happen if you have such system in place. And in some cases, on top of this, you have a polymer gel placed between these two electrodes. So, basically sample is diffusing through this, sample is moving through this polymer gel. So, in some cases polymer gel acts as sieving matrix material in the separation channel. Gel matrix reintroduces a size dependence to the electrophoretic migration. That is, in gel electrophoresis, analytes travel through the porous gel network with smaller fragments experiencing less resistance and eluting faster. Do you understand what a gel is? Hydrogel, it is basically made of water, and small amount of polymer and cross linker is present there. So, these polymer chains, they are cross linked, that means it could be possible that this cross linker that forms some kind of coordination complex between with the polymer. So, there are several dangling chains of the polymers and they are tied together by the cross linker. So, you form a network here, and water remains trapped within this network. So, that is typically a hydrogel. All right. So, that is the gel we see. Now, this, so it has a structure. So, gel has a structure because these chains are already cross linked and water remains trapped within these cross linked network. So, this crosslink network, this acts as a sieving matrix. That means, if the molecule the sample I said contains A, B, C, D, E, F, etcetera, out of them the components that are small, that can move through this network easily, whereas the components which are big, that cannot move through this network. So, you are introducing another size dependence, you are introducing another classification technique within the channel. All right. So, this is basically this is referred as gel electrophoresis. So, in gel electrophoresis, analytes travel through the porous gel network with smaller fragments experiencing less resistance and eluting faster. Now, I want you to think of this the picture that I had here, the picture that I have here. Now, if you invert it this way, you have the electrodes here and the sample is placed in between. So, if you move it by 90 degree, okay, and then you have a laminar flow through this, laminar flow in this direction. Let us don't confuse ourselves with the presence of gel. You have the two electrodes and then you orient them, you rotate this by 90 degree. So, depending on the size and the charge, the particles, as I said, A, D and H would be sitting in at one layer. So, if you have the two electrodes present there and if you have the sample, so they would be attracted to, I said it is moved by 90 degree, right, it is oriented, it is rotated by 90 degree. So, if after some time if you switch off, if you freeze, then this you will find one layer, one band with A, G and H depending on the size and charge, another band with some other components that have similar mobility. So, you will be producing bands within, all right. So, within this channel, and now if you are flowing, if you are having this laminar flow, if you have a parabolic velocity distribution, one layer sliding against the other at different velocity. So, what you will find is you would be eluting layers based on their size and charge, right. So, you will be producing, as I said, fractogram, one size and then another size and then another size, right. So, this is exactly what you call electrical filled flow fractionation. I just now mentioned filled flow fractionation of electrical type, where you have electric field to put the components in bands and then eluting it using a parabolic velocity profile. That is exactly what is electrical filled flow fractionation, and that is what you can accomplish using electrophoresis in a rotated frame. Okay, I would like to stop here. In the next class, I will probably complete this lab on a chip, complete this discussion on lab on a chip, and then we will proceed further on basics of microfabrication. I stop here today.